Hello, I'm Hoppa, and welcome to this presentation. Like many other nations, the U.S. is pursuing renewable energy with plans to build enough offshore wind turbines to power over 10 million American homes by 2030. At the same time, energy sector and critical infrastructure cyber attacks have been steadily increasing over the past 15 years, such as the recent Colonial Pipeline incident. Today, you'll hear about the state of cybersecurity in the wind energy industry, potential risks in offshore wind farms that may impact critical infrastructure, including maritime operations, and some recommendations for what we should be doing now to batten down the hatches. And for all you land lubbers out there, batten down the hatches is a nautical term warning us to get ready for trouble. Here's the obligatory some facts about me slide. I entered academia after a multi-decade career in information technology research and development. I've been at Norfolk State University for about 5 years now. And before that, I taught cybersecurity graduate courses at the University of Maryland Global Campus in Europe. Now I live and work in Virginia Beach, right where the Chesapeake Bay meets the Atlantic Ocean. And both my spouse and my son have maritime careers. You also may be aware that Norfolk, Virginia is the location of the largest seagoing military presence in the world and is part of the Port of Virginia region. So it's only natural that my interests in cybersecurity include maritime concerns. Before we go any further, I'd like to remind everyone that everything I say today is my own personal opinion. And if I mention any products and services, that's all it is, a conversational mention, not a recommendation or an endorsement. Now, I want everyone to pause for a moment and engage in a thought exercise. Think about a time you had to go without electricity for a few hours. Maybe you were on a camping trip from hell, or a substation near your house was struck by lightning, or you visited somewhere that has rolling brownouts. Now think about going without electricity, not just for a few hours, but for a few days, or a few weeks, or even longer. That would be no fun, right? Our increasingly digitized society also means we're increasingly dependent on electricity, not just for luxury comforts like air conditioning, but also things we consider essential, like food refrigeration, pumping gas, water purification, banking, Wi-Fi. The list goes on and on. I think you get the picture, though. Now think. How well prepared would you be to cope with the effects of a widespread, long-duration blackout? How well prepared do you think the nation is? Next, I want you to think about a favorite food or other consumer item you really wanted at the height of the pandemic, but you couldn't get it, not from the store shelves, or even by ordering it on Amazon. That was no fun either, right? Odds are shortages we've all experienced in the past year or so can be traced back to some disruption in the Maritime Transportation System, or MTS, or its subsystems, or associated supply chains that feed or emanate from MTS. After all, about 90% of the goods and services we use every day come to us in whole or in part via ship. Who knew? Starting with this fabulous graphic from Gary Kessler and Steve Shepard's book on maritime cybersecurity, just think about all the moving parts associated with MTS. Such as seagoing vessels and ports and intermodal carriers like railways and trucks and aircraft and manufacturing and so many others, and the ripple effects that occur when something goes sideways anywhere in this ecosystem. And guess what? Electricity is essential to these complex supply chains too, that enable our American way of life. For communication and the business systems that support them. And well, again, you get the picture. MTS depends on electricity too. Right about now, I'll bet you're thinking, what is she talking about? Am I listening to the right presentation? I thought we were going to hear about wind farms, and so we shall. But first, I had to establish a rationale for why we should even care and spend time during a session talking about offshore wind farms, other than just acknowledging them as one more thing we might find out in the ocean. If you're like me, I didn't even know from offshore wind power as recently as 6 months ago. But then I was approached to lead a summer research team of 4 college students. And our task was to look at potential cybersecurity risks in offshore wind farms. And I must admit, this was a new one on me. But I did some quick reading, and suddenly I realized how critical infrastructure like the electric power grid and MTS and offshore wind farms all might come together in some very unpleasant ways when we consider them through the lens of cybersecurity. And this has proven to be something quite interesting to explore and think about. And okay, maybe it's even keeping me up at night a little bit too, but let's not dwell on that part. So now we need to cover a little wind farm 101. So we're all at sea level in our understanding of some basics. That will make it easier later to understand cybersecurity risks in relation to offshore wind farms and maritime concerns. Remember, this is just an introductory presentation and our time is limited. So we have to keep things at a fairly high level. Now you can visually follow along the narrative by looking from the left to right across this graphic. Wind forms when air moves from high pressure to low pressure areas in the atmosphere. Wind flow patterns and speeds greatly vary across the land and are affected by bodies of water, vegetation, and other terrain features. Wind rotates the turbine's huge blades that can be over 100 feet long. The turbine is attached to a rotor shaft mounted upon a tower or mast that can be as tall as 350 feet. The rotor converts kinetic energy into mechanical energy by spinning generators that create electricity. A transformer is then used to increase the voltage of the generated electricity. As it travels along distribution lines, the power is reduced to safe consumer usable levels. And that's how end user homes and businesses get electrical power from an onshore wind farm. Now, offshore wind farms have some common operating principles with these onshore wind farms, but they're much more complex. For one thing, even though onshore wind farms are located in remote areas away from population centers, offshore wind farms present even more logistical challenges, since to build and maintain them, as you can see in this simple graphic, the turbines communicate with each other using an industrial control network called SCADA, and the generated electricity is eventually fed into the electric grid through underwater and underground cables. There's 2 substations in between, and there also are control centers for both the grid and the wind farm. The 2 centers communicate with each other to help regulate the electricity flow. The wind and its control center also communicate with other to receive and interpret performance and sensor data like weather and performance of the farm. What's really important to note here is how many communication pathways there are. All those lines shown in blue are potential cyber attack opportunities. And because of the distances involved and the impracticality of running wired communication in the harsh sea environment, for the most part, we're talking about are highly hackable. So with that basic understanding in mind, you still may be as surprised as I was to learn that last year, around 8% of all electrical energy in the US was generated by onshore wind farms, and about that same percentage held globally. But what about offshore? Right now, worldwide, just 0.3%, that's 0.3% of all electrical needs are fulfilled by offshore wind. And most of that is happening in Europe. On the right side of this slide, I've listed the US offshore wind farms that are in various stages of planning or development. As you can see, there's about a dozen, and they're concentrated in areas with the highest offshore wind speeds. Makes sense, right? Because more wind means more potential electricity can be generated. Of these US wind farms, only the first one on the list, that's Block Island, is actually watts, enough to power about 17,000 homes. The next one, Coastal Virginia Offshore Wind, or CVOW, which is about 30 miles away from my house, has a couple of turbines functioning, but it's just in a pilot phase at this point. The Biden administration has announced a goal that by 2030, all these sites are going to be complete and online. If that succeeds, these farms will be powering over 10 million American homes. Now, keep in mind, there are about 132 million US households total right now. So these offshore wind farms would service about 8% of them. So now more about the cybersecurity part. Offshore wind farms are being built using the same operational and information technologies that are used in onshore wind farms, which means they're vulnerable to similar cybersecurity attacks. And we have already documented cases where onshore wind farms have been hacked. I've shown a couple of examples here that were controlled experiments. And what's really scary about them is how little effort and expense it took to undertake successful attacks. Basically, a pair of bolt cutters and a couple of $100 of electronic equipment bought at Radio Shack. Another scary thing I'll share with you is this. This summer, as I mentioned, I worked with a team of 4 college students, none of whom had any background in cybersecurity or wind farms. After investing about 3 weeks of reading time, using everything freely available on the internet, about 250 hours total, these students were able to come up with some very plausible scenarios for how offshore wind farms could come under cybersecurity attack, or could be used as stepping stones to attack other critical infrastructure like the electric grid or maritime assets, such as vessels or ports. We started our analysis by thinking about who would be the most likely threat actors to attack offshore wind farms. We noted that while there are known attacks that are likely to work, given the complexity of the offshore infrastructure and the physical location of the turbines out in the ocean, this kind of undertaking would require significant long-term planning and technical expertise. That earmarks well-provisioned hacktivists and nation-state actors as the most likely attackers. Why would hacktivists want to do this? Well, a lot of people aren't happy about offshore wind farms. They think they're unsightly, or they'll have a bad side effect on things like commercial fishing or recreational boating or the environment. So well-organized hacktivists may like to disable or even blow up wind farms to make statements to that effect. What about nation-state actors? Well, as the US becomes increasingly dependent on wind energy, adversarial nations will see this as an ideal way to cripple us. Remember that thought exercise we did at the beginning of this talk? How many days do you think it would take for a widespread blackout to cause significant civilian unrest? Not to mention the chaos that would result as banks and gas stations and stores and military bases and so on, so many other enterprises would be unable to operate without electricity. After we considered the who's and the whys, we had to work through the how likely threat actors might use, followed by the consequences or impacts that would result when those attacks are successful. I want you to have this slide as a takeaway because it highlights on the left side many possible attacks, whether by directly accessing the wind farm or its infrastructure, or by indirect access, that is, remotely injecting malware using those many vulnerable communication pathways we looked at earlier in the simplified offshore wind farm graphic. It's also important to note that multiple wind farms will likely be managed by each single control center, which means an attack on one offshore wind farm can move laterally to additional wind farms, broadening the scope and impacts of that attack detailed on the case of this slide. As you can see, there are decidedly kinetic effects in some cases. For example, turbines can be blown up or made to operate wildly and catastrophically fail, littering the waterways with debris. Cyber physical effects include disrupting wind farm operations so that the flow of electricity to the grid is significantly reduced or interrupted, potentially producing a brownout or a blackout. My team of college students worked through as many as a dozen viable scenarios where offshore wind farms are part of a cyber or cyber physical attack with potential impacts on critical infrastructure and maritime operations. This graphic depicts one such attack. We've been able to confirm each step along the way based on past documented hacks, the many exploitable communication pathways, and by informal verbal confirmation from subject matter experts. The likely threat actors will target the control center. They'll remotely hack in through externally accessible communication pathways, or by tricking, bribing, or even blackmailing an inside employee with the right credentials to gain access. They'll escalate privileges on the resident systems and use the center's ability to issue commands to the farm to insert malicious commands aimed at the local area network, connecting and controlling the farm's turbines. The hackers then own the system. They can shut down the farm, creating a brownout or a blackout, a critical infrastructure impact, in other words. This also may impact maritime concerns in the blackout area that depend on electricity, such as port operations. Or the hackers could issue commands that make the turbines spin out of control, even to the point of catastrophic failure. Imagine 250-meter tall towers toppling over, flinging 100-meter-long rotor blades over thousands of square kilometers of ocean. The resulting debris not only could cause loss of life and property damage to nearby structures and vessels, but also could create hazardous conditions in waterways that will impede shipping, port access, and coastline defense. As I mentioned earlier, all indications are that we're not doing anything fundamentally different in offshore wind farms than onshore wind farms, which means they're inheriting known cybersecurity flaws. So this also is causing worries for the maritime industry and seagoing military services. Vessels have traditionally relied on an air gap to provide cybersecurity. That means they were floating information islands that used isolation to protect their automation assets, security through obscurity. But modern vessels are connecting in big ways, not just through satellites for communications and navigation and ship-to-shore links for business transactions, but also due to the myriad of handheld mobile devices and personal computers that virtually every crew member and temporary worker brings on board with them. And offshore wind farms present what cybersecurity professionals call a lateral attack platform. The red pathways on this graphic trace how a hacker could infiltrate the wind farm's infrastructure, maybe using a drone or a small vessel sailing nearby, to implant a capability to broadcast malware to nearby vessels as they pass by and infect them. Those vessels would transfer the infection to the ports they enter as soon as their infected systems start communicating with shore-based systems. Alternatively, hackers can hopscotch malware from ashore systems to the import vessels. And then once those vessels get underway, they can be used to infiltrate other vessels and ports as well as the wind farms. This latter attack scenario actually has a name called the Shen scenario. This slide is a list for you to ponder later. It will help remind you why securing offshore wind farms is such a challenging problem and why we need to be working on it sooner rather than later. Particularly troublesome is the list of all. These are like open doors, inviting hackers into the maritime ecosystem. They just need to find one way in. And from there, as illustrated on the previous slide, they can hopscotch to higher value targets. Here I've enumerated some of the known vulnerabilities in industrial control systems, or ICS, that we have to assume are present in offshore wind farms. I say we have to assume that they'll be present because, unlike our legal system, where guilty parties are presumed innocent until proven guilty, in our cybersecurity practice, we have reached until that known patches have been installed and all known hacks that take advantage of the patched vulnerabilities are no longer successful. And even then, we never say a system is 100% secure. There's no such thing because new vulnerabilities and attacks are constantly emerging. We're playing a risk mitigation game here, and it's us, the good guys and gals, against them, the malicious hackers. So what I'm saying is we have not found adequate evidence up to this point that common vulnerabilities, such as the ones listed here, have been addressed in the offshore wind farms that are currently being built. Now, I've listed here some well-known good cyber hygiene measures for both ICS systems in general, as well as wind farms in particular, whether those wind farms are onshore or offshore. We should probably add to this list some changes in standard operating procedures, especially the actions of human personnel involved in running and maintaining these systems. Humans remain the weakest link and often will be exploited as key elements in successful attacks. The recent statistic I've read is that over 90% of all successful hacks today involve human hacking or social engineering as one very important step. Let's be honest, all the changes listed here are great and they're recommendable to do. And all these actions are still needed since it's clear at least some of them are not yet standard practice across all wind farms. Fixing these easy things will not keep out sophisticated hackers, but it will slow them down. It truly is a Band-Aid, as I've suggested at the top right of this slide. Here are some additional actions the wind industry should be undertaking now. We all should be concerned that it can take nearly a year to patch known problems, and even more so that outdated, unpatched components may be propagating into the emerging offshore wind farm landscape. All the things listed here make sense to do, but perhaps the most challenging is finding the right experts to do the job. ICS cybersecurity is an extremely niche skill set. And just like every other segment of cybersecurity, with hundreds of thousands of jobs going unfulfilled globally, if we believe the statistics, and I personally do believe them, the industry should consider partnering with academia and commercial trainers to help create this specialized workforce that they need. After all, if they have all kinds of unfulfilled jobs, then what are they doing with the salaries they aren't paying to those non-existent individuals? Why not use that money to fund security-focused studies? The students that are funded can then commit to working for those companies during breaks and for a few years after graduating. In other words, instead of waiting around for well-qualified employees to appear out of nowhere, which obviously is not happening, why shouldn't the question? To be fair, there are many challenges in academia as well. As I just mentioned, we're talking about a very specialized skill set here. It takes a researcher a lot of effort to gather up state-of-the-practice knowledge and get up to speed sufficiently to make contributions. Mostly because what has been done to date is all over the place. So knowledge consolidation will certainly help. And academia also needs to be willing to partner with industry to offer trainings that will build the workforce the industry is seeking to meet their needs. In other words, we academics have to build an employable product. I'd also like to point out it's very risky and difficult to do cybersecurity penetration testing or repairs on the fly to critical infrastructure like wind farms and other elements that feed the maritime industry once those systems go online. So we need capabilities like test beds and computer models that allow us to conduct these kinds of investigations under. So we've covered a lot of ground. Here's a roll-up of the key takeaway points I hope you'll remember from this presentation. Up to this time, efforts around offshore wind farms have focused on matters like selecting the right sites, garnering public support around renewable energy, and assessing environmental impacts. Cybersecurity is recognized as a concern, but it's been put on the back burner because the likelihood of an attack right now is viewed as being low. There just isn't much there to attack as far as offshore wind farms are concerned. Not undoubtedly are not sitting idly by. They're taking advantage of this window of opportunity, this lack of urgency on our part. They're probing the attack surfaces related to offshore wind farms. I assure you, they are a lot more skilled than myself and my student team were this summer. And remember how quickly this team got up to speed. It only took those students a few weeks to figure out some viable attack scenarios. Hackers for hire may even be implanting advanced persistent threats and malicious insiders in the wind industry right now for future activation. Research, development, and implementation of offshore wind farms that are hardened to resist cyber attacks should be priority activities right now, both to lower the risk of future attacks occurring and to lower the likelihood those attacks would eventually be successful. If you're interested, and maybe even a little frightened by these thoughts, here are some resources that can help you learn more and stay plugged into this problem space. I especially encourage you to read the DoD Roadmap for Wind Cybersecurity. This will give you a big picture sense of where national entities are and research labs are in terms of addressing this overall problem. And now, based on what you learned today, you can mentally compare where they are against where you think they should be. If you're interested in the nuts and bolts of cybersecurity assessment and defense, I also encourage you to look at the MITRE Ingenuity resources listed here, like Attack and Defender, especially since they've recently created industrial control versions of these tools. I'd like to thank you for your attention and your interest in this important topic. Please check the schedule for any real-time Q&A sessions. And in addition, I welcome your electronic comments and follow-on questions anytime. Feel free to email me at the address listed here and mention OWF or offshore wind farms in the subject line.